Welcome back again. Olaleko is my name. This is landmarks and acquisition under Morphometrics analysis. Last time I briefly discussed the landmarks, Morphometrics concept, where I discussed two types of morphometrics, traditional and geometrics, and I also discussed some applications of morphometrics. And this time I want us to look at a landmarks and acquisition theoretically. Okay, in this particular one, we'll be covering definitions of landmarks, type of landmarks, all right, homology of landmarks, landmark acquisition, tools, measurement errors with procus and nova. Okay, so what is landmark, or what are landmarks? Landmarks are points of correspondence on each specimen that match between and within populations, or equivalently biologically homologous anatomical loci recognizable on all specimens in the study. All right, from my right hand side here, you see two images here, A and B. In the A, you can see there are landmarks on the face of the object here, and these landmarks are mixture of both anatomical landmarks and semi-landmarks. All right, and in the B part here, this is purely anatomical landmarks. There are no semi-landmarks here. All right. So we can point out some biological landmarks here from this particular A, though they are mixed together with semi-landmarks. But we can still locate, you can still point out, for example, this and this, this and this. They are all biological landmarks. All right. Landmarks can be anatomical landmarks, okay, because we have anatomical, we have semi-landmarks. So anatomicals are points assigned by an expert that corresponds between organisms in some biologically meaningful way. I mean meaningful way because it must be meaningful biologically. From the fish you are seeing here, you can see there are landmarks here that it determines some distances or length between one point to another point. From there we have head length here because of the landmarks regions from here, from this place to this place. So when you trace it down from the stroke of the fish here to this particular point here, you can find this landmark of the head distance or length of the fish. The same thing happens to the dorsal fin base length here, from here this distance here to this distance here, because there are landmarks here. The same thing happens to this dorsal fin length here. So these are called biological landmarks, or otherwise called anatomical landmarks. In the human face here, you can see some landmarks here that are biological. We can see endocanton left, exocanton left, celion, exocanton, endocanton here. We can see pronace here, subnace, alare left, alare right, okay, chelion, naton, and the rest of them. You can see they are all landmarks, which is anatomical landmarks, which must be pinpointed by an expert because they must be meaningful biologically. All right. We now have semi-landmarks as well. Okay, semi-landmarks are points placed arbitrarily using an algorithm, often by defining endpoints at a biologically homologous point and placing a specified number of landmarks between them. So we also have this semi-landmark can be mathematical or otherwise called geometrical. It can also be pseudo-landmarks. Mathematical points are the point located on an object according to some mathematical or geometrical properties. For example, high curvature of an extreme point. And so the landmarks are constructed points on an object either on the outline or between landmarks. Okay, so we have a type 1, type 2, type 3 landmarks. Okay, the type 1 landmark is totally called anatomical landmarks, which we looked at previously, otherwise called biological landmark. But the type 2 landmarks are mathematical landmarks, okay, which I just described now. And these mathematical landmarks also are location of the point defined by obvious geometry, okay, which I explained before, that a point of greatest curvature. And the type 3 landmarks, which is pseudo landmarks, also is location of point defined by reference to another point. For example, point ventral to last tooth. These are landmarks. But at the same time, we also have what they call semi-landmarks that are slid, which we are now calling sliding semi-landmarks. These are slid on the surface, on the curves. The position of semi-landmarks can be optimized by sliding them along the outline curve of as part of the Procus analysis to provide the best fit between shapes. Okay, these are called sliding semi-landmarks because they are slid on the surface, which is mostly done automatically by minimizing either bending energy or Procus analysis. So we have an image here, or two images here. They are the same image, but they are slid, okay, on the surface of this particular specimen. You can see there are many points here. All those points here you are seeing in blue, they are called semi-landmarks, but they are sliding semi-landmarks, while the red colors here are called the anatomical landmarks. All right. So we have what they call landmark homology. I mean the homology rules of landmarks, which means each image must have the same number of landmarks. You can see if you have 100 images or your specimens, they must have the same number of landmarks on each specimen. If this one has 13 in numbers, landmarks here, the specimen B must have 13 in numbers. Specimen C the same thing, D the same thing, and on all specimens. All right. And if you have the landmarks on each image must be in the same order, which means they must follow the same pattern. If you have one here, you must have one here. If you have two here, you must have two here. And the same thing on all specimens. They must follow the same pattern, the same order. And landmarks are ordinarily placed on homologous points that can be replicated from object to object based on common morphology, common function, or common geometry. And this means these landmarks must be seen on all specimens, which must have the same morphology and common function. So it must be visible on all specimens. And we have acquisition tools in two-dimensional, and apart from the rulers, calipers, and goniometers that they have been using previously, there's now a wide spectrum of more advanced technology available. For example, we have TPS-dig, we have ImageJ, we have Scan Image, we have Mathematica, we have RGeomorph, we have RStereomorph, we have Mobius, and so many others that are used to collect landmarks in two-dimensional. Okay, we can see more in this link written here. I will post this link also under the video where you can click and download or read more about those tools mentioned there. And we also have a acquisition of tools also in three-dimensional. Okay, and they are based on techniques and cost for extracting 3D landmarks coordinates, which vary depending on the size of the specimen. We have reflex measurement microscope for small specimens, and we have 3D scanners, microscope, digitizer, mesh lab, philolimbus, RGeomorph, head warp, viewbox, checkpoint, and MRI or CT scans for large specimen. They are all potential options. Okay, you can see a sample of reflex here microscope here. You can see a sample of microscope robotic arm here, a sample of next gene laser scanner. All these ones, they are majorly old methods actually, but we have more advanced methods which can just use computer to do easily with cameras. So because we now have 3D cameras that can perform better now than just all those old methods. So these are landmark acquisitions in 3D, and we have what we call measurement error of landmarks. How do we measure landmark errors? All right, because the process of extracting landmarks coordinates will always be associated with some degree of measurement error. This can result from inconsistent tilting of specimens relative to the plane of digitization, or non-coplanarity of landmarks, or difficulty in pinpointing the landmark locus, or even a difference in illumination or focus. All right, image distortion on the screen can also introduce non-biological signal, and we must understand that a measurement error can be minimized by carefully mounting photographs and landmark selection, but can never be totally eliminated. Okay, so that is the reason why we must account for landmark errors. So measurement error is defined as the variability of repeated measurements of a particular character taken on the same individual relative to its variability among individuals. The overall measurement error in shape analysis is traditionally dissected relative to imaging, that is, the differences in pictures of the same image. For example, if a picture is captured in the morning, the same picture is captured in the evening, so we have the lighting and darkening one. You can now you can account for the errors okay, between the lightning one and the one that is captured in the night. That is a imaging error. We also have digitizing error. That's error as a sort of pinpointing the landmark locus, okay, because human beings are not always accurate when it comes to pinpointing of landmarks using hand, and that is why we have to account for differences in landmarking the same of the same image. So that is why we use the same image. So you have to pick some images, for example, and landmark them several times to account for the variability among individuals. For example, there are three ways to actually go about this. You can have a observant base, okay, where you have like maybe 2 or 3 operators that landmark the same specimen. If you have 100 specimens, each of them landmark the same number of specimens on different machines, okay, and they later bring the result together, and they now use to account for the errors, the digitizing error, because each of them will always have some kind of error that because they can never be the same. So you have to look at the variability among the individuals from those 3 operators. So in that case, you now have a device error accounted for at the same time. You have to, because the devices you use is not the same, so you have to account for device error as well. And also you can have the same operator can digitize the same specimen on the same machine, maybe many times, 2 or 3 times, and then account for the errors, okay. At the same time, you can also have the same operator taking few images from the total entire images and now digitize those images to represent the error image, represent the entire image. So for example, you have 100 images. For example, you can take like 10 images randomly, select 10 images, and you can digitize the images twice or 3 times or 4 times or 5 times to account for the variability among individuals, so that you can now account for what is called landmark error or error of digitization. So this is called measurement error in digitizing, which you can never be eliminated. It must be accounted for at all times. So today I'll be stopping here for now, and in the next teaching or video we start practical analysis, how to collect our landmark data using different tools, which will be seen practically from next video. So I want to thank you for watching this video. You can subscribe for the video, you can like, you can also share the videos for other people to enjoy the video. So I will see you in the next video where we start the practical aspect of the landmarking process. Thank you so much for watching. I will see you later.